Hi there, welcome to the third week of this course. Hope you have been enjoying the course so far. So we are into the third week and slowly we are getting into more sophisticated topics. So in this week we will see a lot of new things. So I hope that you have been able to spend some time over the last 2 weeks on this course. So there is a lot of activity on the forum, asking questions and lots of things. That's a good thing. So continue doing it, and whenever you get stuck on the forums, please email to the forum. So one small request that I have to all the students is that if you are going to post anything new, just go and do a search on the forum first if somebody has already posted on this topic, and if somebody has already posted, then just go and add to that specific email. Otherwise what happens is we see too many emails and it's very hard to track whether all these things are replied back or not. So I have been marking many of these things as duplicates over the last 2 weeks. So but this is just a small request to all of you that you go and search for questions that you are asking on the forum first. If somebody has already asked that question, go and add to that discussion rather than opening a new post. The other thing that I want is sometimes you are posting on the forum and the subject line has no relevance to the contents that you are posting. So it is better that the contents that you have and the subject line of the emails should match. So don't go and hijack another thread and go and ask a question which is not relevant. The third thing that I wanted to say is some of you have been answering some of the questions from homeworks right in the post itself, and those are deleted without even informing you. So this is not in the spirit of the course. So you can help to the level that people can understand the material, but giving away solutions is not acceptable on the forums. So I have been deleting some of these emails without ever informing you about that. So anyway, given all the other things, I hope you are able to spend time, most importantly, and you are able to understand the material that is in the course. So one another thing that you would have noticed is the videos are now available online. So you can go and download the videos also now, and that I have already posted in a forum, so please take a look at that also. So let's move on to this third week's lectures. In this week we are going to see combinational circuits. So we'll start with combinational design to begin with. So combinational circuits are essentially circuits in which output depends only on the current set of inputs. So there is no notion of history that is associated with combinational circuits. The current output depends only on the current set of inputs, not what kind of inputs were given earlier and what is the state of the circuit earlier and so on. So a combinational circuit is usually one in which there is no feedback path in the circuit itself. You will never see an output of a gate connected to somewhere else which forms the input path. So you will see inputs feeding a certain set of gates, from there you get another set of gates and so on all the way to the output, but nothing that is going to feed back from output back to the input. Actually at any intermediate level you will not see any wire that is connecting to somewhere in the previous steps. So all the basic gates that you have seen so far, like AND gate, OR gate, NOT gate, XOR, XNOR, all of those are actually combinational basic circuit blocks. They are all combinational in the sense you give inputs and you get current outputs. These form the basic gates for combinational designs. So let us see how to design a combinational logic circuit. So the first thing we need to do is to be able to understand the problem. So you are usually given problem in English description. So even though in the course I have been giving equations directly, in the real world most often you will be given a design problem which is given as an English description. You first have to understand the input and output behavior of it, and you identify what are the inputs, how many inputs are there and so on, and draw a top level block diagram if it will help you. So sometimes pictures are very useful to understand what you are supposed to do. Then you go and formulate a standard representation. You go and write either the truth tables or Boolean equations. So whatever is comfortable for you, do that, and once you are done with it, then you can choose the implementation. So you can either choose discrete gates. So I am sure in your digital circuit labs you would probably pick up 74 series chips and connect them together, or if your labs have access to FPGA based devices, you are going to take the circuit that you have designed and put it down on the FPGA boards. So either way you need to decide what kind of implementation you are going to do, and finally apply the following design procedure. So take the representation, minimize the level of hardware that you have, and go and implement the algorithm. Go and check whether your circuit works correctly by doing simulation, and finally implement it on the device. So this course will teach you the first two bullets, namely how to take a problem, represent the problem, minimize it, implement it algorithmically. We will also see how to simulate and check whether the design is correct or not. For this we will use Verilog, and the final implementation is not something that I am going to cover in the course. So this is beyond the scope of this course. So for that we actually need real hardware with which we can do things. So let us take a small example problem. So this is a design problem where it is a process line control problem. So imagine there are steel rods coming out from a steel plant, and they are supposed to be of a certain length, let us say 100 centimeters in length, right, 1 meter length, and what you want is the rods could be plus or minus 5% in length, and that is acceptable for the engineering problem that you have, but if it is beyond that you want to throw it away. So the industrial process is good enough, it gives you rods which are not too big. If you ask for 1 meter, it is not going to give you a rod which is of 2 meters or let us say 0.5 meters and so on. The rods come in the range 110 centimeters to 90 centimeters. However, the acceptable range is let us say 95 centimeters to 105 centimeters. We want to be able to detect something like this and throw away the rods which are outside the range. So this is the design problem. So you want there is a margin of error, plus or minus 5% is acceptable, but beyond 5% is not, either minus 5% or plus 5%, beyond that is not acceptable. And we know that the rods are controlled, and the rods are not too small or too big in length, they are within plus or minus 10% anyway. So what we need to do is reject the plus 5% to plus 10%, also reject the minus 5% to minus 10% rods, and we need to come up with a circuit for that. So this is the design problem, and so imagine the set of rods like this. So let us represent the length of the rod along this vertical axis, and let us say this is the line from which you are measuring, imagine a line at the bottom from which you are measuring, and let us say this is the spec, whatever length that is, some spec. So I said 100 centimeters, so let us keep it as 100 centimeters from here to here, and so this plus or minus 5% are this band. So if it is plus 5%, if you measure from here, this is 1 meter plus 5%, if you measure from here, this is 1 meter minus 10% and so on, and this one is 1 meter plus 10%. So I know that no rod will be greater than this length. If I start measuring from here, it will not be more than 10% of the expected length. So this rod is too long because it is above 5%. This rod on the rightmost side is too short because it is below 5%, whereas this rod here is within the spec. So from this second line here, from the second line here to the fourth line here, if the rod is within that, it is within spec. So I want to design a control process to do this. So one way in which we can do this is put sensors here and put enough sensors here to see whether this rod is of a specific length or not. So imagine some sensor which is from this side to this side, and let us say I shoot a beam from here to here. If there is a rod, the beam is blocked. If there is no rod, the beam is not blocked. That is what I am going to do. Similarly here, if the rod is sensed, right, I am going to see something. If the rod is not sensed, I am going to see something else and so on. So I can put sensors on two sides to check whether the rod is in this belt or not. So I am going to imagine rods coming in belts, like conveyor belts, like you would have seen in movies and whatnot, or if you have been to factories you would have seen this. So you see a belt in which you place something and this keeps moving along. So I am going to imagine that the conveyor belt keeps moving along. At some point there is a sensor which is going to sense the rods or not, and we need to place enough sensors. So the first question is, how many sensors should we place to detect if there is a rod or not? So let us imagine something like this. The rods are going to move in this direction, and what we are going to do is, at some point we need to detect whether whether the rod is there or not. So I am going to place in this example 3 sensors. The first sensor I am going to call it A, I am going to place it here, and I am going to place 2 other sensors, namely B and C. B I am going to place it at minus 5% line, and C I am going to place it at plus 5% line. So I am going to place 3 sensors. So I could place sensors here, here, here and so on, but for this problem I know ahead of time that these 3 sensors are enough. We will see why these 3 sensors are enough in a little while. So I am going to place 3 sensors and I am going to draw a truth table. So from a problem description we identify the set of inputs. So now A, B and C are 3 sensors which are going to give us 1 or 0, and if A gives a 0, it means that there is no rod detected in the line of sight of A. Similarly, if B gives a 0, there is no rod detected in the line of sight of B, and if C gives a 0, there is no rod detected in the line of sight of C. So let us see how to detect whether there is a rod first of all, and if there is a rod, then how do you reject it if it is beyond the range that we do not want, right. So let us first see the case. So if A senses no rod, B senses no rod and C senses no rod, it means the rod, I am imagining that it is coming from the top to bottom, there is a belt running from top to bottom. If none of the sensors sense a rod, then it means that the rod is not even available, there is nothing you can reject there, there is no rod, there is nothing to reject. So if A senses, if A does not sense any rod, B does not sense any rod and C does not sense any rod, we have there is nothing to do, we are not rejecting, there is nothing to do, so it is a 0. Then if, so this is the case where the second case, A senses no rod, B senses no rod and C senses a rod, right. So which means the rod has just entered from the top and it has crossed this sensor C, right. If it has crossed that sensor C, at this point you still cannot decide whether the rod is supposed to be rejected or not. So in fact, to decide whether the rod should be rejected or not, it is not only enough that it has crossed C, it should have crossed B and it should have come to A. Only when it comes to A, you can really make a decision whether you want to reject the rod or not. So you can see that when C is on, we can't do anything about it. When B is on, the rod has not reached A. Even if both B and C are on, the rod has not reached A. So when A turns on, you can see that that is in the bottom 4 combinations. When A turns on, we are going to make some decisions. So let us see what these decisions are. So the first case is, in A the rod is sensed, but in B it is not sensed and in C it is not sensed, right. So if you are sensing it in A and if it is not in B and not in C, it means that the rod is shorter than 5% of the target length. So my target length is here, so if it has crossed this minus 5%, it should have been within 5% of that, at least it should have crossed this line, but in this case it is not. So imagine this as 94 centimeter rod, so this is the 95 centimeter line, this red line is 95 centimeter line. So if this rod is only 94 centimeters, A would have sensed it here because you are measuring from A, but B would not sense it and C would not sense it. So in this case 100 means it is a short rod, so rejected. So if you want to reject, we are saying reject means 1. Then let us look at the second case. A senses a rod, B does not sense, but C senses a rod, right. So if we imagine that there is only one rod in the belt at any point of time, we cannot have a single rod which is sensed in A, not sensed in B, but again sensed in C. This is not going to happen. So this is a don't care condition, this will not happen, so it is a don't care condition. So remember, this don't care makes a lot of sense here. It is not 0, it is not that we are saying we are not rejecting it, right. We are saying that this condition cannot happen. So there is a difference between putting a 0 versus putting a X. Then finally if I have 1 here and if I have 1 here, what that means is A and B are both sensing the rods, but C is not sensing. So that is this row here 1 1 0. So this is correct, this is a rod that we want, right. It's in spec. So this rod is from measured from A, it has passed the B line, but it has not touched the C line, so it is acceptable. But if it goes from A, touches B and touches C, this is a rod which is more than 5% of the target length, you want to reject that because it is too long. So now this is a truth table. So starting from a problem, we have come up with a truth table which actually gets what we want. If you think about this, now once I give this table, in hindsight you can go and think about whether you really need these sensors at minus 10% line, at the spec line and plus 10% line and so on. So what we need is, we need to be able to measure something below 5% and something above 5%, and all the other things are clear whether you want to accept. So in this range you accept, beyond that you reject, beyond this you reject. You are looking at ranges. So there are 3 ranges, from this one to minus 5%, from minus 5% to 5%, and plus 5% to anything above plus 5%. Right? So since there are only 3 ranges, 3 sensors are enough to see whether they are in the ranges. That is how I decided three inputs A, B and C. So you can go and think about this and justify the fact that 3 sensors are enough, and you can also go and think about whether just 2 sensors are enough or whether you need 4 at all. So I know, so I knew this ahead, but you can go and think about why 2 is not enough for this problem and why 4 sensors would be too many. So once you have this truth table, you know how to do Boolean minimization. In this example, it turns out that the minterms, so there is 4 and 7 which are on, and 5 is a don't care. So you combine them together, it is A into B bar plus C. So an English way to represent that is, you should sense it in A, and either it should be sensed in C or it should not be sensed in B, in which case you should reject this rod. So that is the way I would interpret it in English. I should sense it in A, which means the belt has come this far so that I can start making the measurement, and either I sense it in C or I do not even sense it in B. If that happens, then the rod is rejected. So this A B bar gives the condition that the rod is too short, and AC gives the condition that the rod is too long. So if it is either too short or too long, you want to reject it. So that is an English way to say what this whole thing is about. So you could have actually done this even ahead of time without doing any of the tables. You might have written this directly also. So if you get the intuition for solving a problem like that, please go ahead and do that. But this gives you a systematic way in which you can approach the problem. That is all. Okay. So now let us go and look at building blocks for various combinational circuits. So we are going to learn about 4 different building blocks, namely decoders, encoders, multiplexers and demultiplexers. So let us start with decoders. So a decoder, or in general, so decoder is a general term. I am going to use the specific binary to decimal decoder. A binary to decimal decoder will have n inputs and it will have 2 power n outputs. So many times we will call such decoders n cross 2 power n decoders. Right. So if you have n inputs and 2 power n outputs, we will call them n cross 2 power n decoder, and each input represents a min term. So we have, in this case we have 2 inputs. So we have 1, 2, 3, 4 combinations. So there are 4 combinations for this 2 variable thing S1 S0, and the output corresponds to the min term that appears in the input is asserted. So you go and look at this. So a decoder, this has 2 inputs and 4 outputs. So this is a 2 to 4 decoder, and in a 2 to 4 decoder there are 4 combinations of inputs. There are 2 inputs but 4 combinations that the inputs can take, and the output tells you which of the combinations is in the input. So if D0 is on, then the input that is given is 0 0. If D1 is on, then the input given is 0 1. Then if D2 is on, the input given is 1 0. If D3 is on, then the input given is 1 1. So you can think of this as somebody gave you an input code and you try to detect which of the inputs was given, right. So that is why it is called decoding. The input is a code, it is smaller in size, the output is more number of outputs than the inputs, right. So this is called decoding. So if you place 0 0 here, this one will turn on. If you place 0 1 here, then D1 will turn on. If you place 1 0 here, then D2 will turn on, and so on, right. This is called a decoder. Let us see how to build a decoder like this. So there are decoders which also have enable inputs. So some decoders have enable inputs. In this case, enable is an extra line. When enable is on, it works like the decoder that I talked about. If enable is off, no matter what the inputs are, then the output is kept at 0. So if you have all 4 of them to be 0, so when the enable is off, all 4 of them will be 0. So we cannot track what the inputs are. So this is a decoder with an enable line. So if you see the picture that I showed earlier, it didn't have the enable line coming in. So there are 2 inputs and 4 outputs, but generally what you have is you have something with the enable. However, you don't count this as in the number of inputs. You still call this a 2 to 4 decoder. So it's 2 input bits decoded into 4 separate lines. So you don't say it's a 3 to 4 decoder. Enable is implicit. You don't count the enable towards the number of inputs. Now let's go and see the internal structure of a decoder. So internal structure is something like this. You want all the possible minterms essentially, right? So if you look at the table, you want 0 0 is a minterm, 0 1 is a minterm, 1 0 is a minterm, and 1 1 is a minterm. The first thing we need to do is to be able to generate all the minterms. So this is the way to do it. So you have S0 and S1, and let's go and look at this gate initially. So this takes S0 complement and S1 complement and ANDs it. So this is S0 complement, S1 complement, and there is a line that is coming from here which is enable. So D0 is S0 bar, S1 bar, enable. That is what this line is, right? And this one you can notice is taking, so you can see that this is S1 which is given in the complemented form, and you also have, so if you notice this line, that is enable, and this one is S0. So if S0 is on, S1 is off, then D1 turns on, that corresponds to minterm 1. So then S1 is on, S0 is off, that corresponds to minterm 2, so line 2 turns on, and if both of them are on, line 3 turns on. In all these cases, if enable is off, if enable is 0, you can see that all the AND gates are getting this line directly, so the output will all be 0 if enable is off. For this to work like a decoder, enable should first of all be turned on, and you will give one of these combinations, and one of the lights will or one of the outputs will turn on. So if you put an LED here, exactly one of the lights will glow if enable is turned on. If enable is off, none of the LEDs will glow if you put LEDs in the outputs. So there is no specific symbol for a decoder. Many times we use this symbol here where we have n inputs and an enable line, and so these are marked from S0 to Sn minus 1. The number of outputs will be 2 power n, not 2 power n plus 1, do not count the enable, 2 power n, and they go from D0 to D2 power n minus 1. So this should have been a D0, I am sorry about that, this should have been a D0. So D0 to D2 power n minus 1. So there are so many of them here. So this is a n to 2 power n decoder. So let us see how to build a 4 to 16 decoder using 2 to 4 decoders. So this is a logical problem. So I am giving you an infinite supply of 2 to 4 decoders, and I want you to build a 4 to 16 decoder. Let us see how to do that. So I am first going to write the truth table required for the 4 to 16 decoder. So what should the 4 to 16 decoder do? If it's a 4 to 16 decoder is one in which you have 4 inputs and it should have 16 output lines, right? That is what a 4 to 16 decoder is. And on top of that you will have another extra line called enable. So if enable is on, then it will work like a decoder. If enable is off, the output should be 0. Let us see what this means. So if I have A, B, C, D, so all the 4 inputs for the 4 to 16 decoder are 0, and if enable is on, then this corresponds to minterm 0. Then similarly if I have A and B as 0 0 and if C and D are 0 1, this corresponds to M1 and so on. So we know that if I enumerate this, since we are figuring out which minterm is on, we will have it from M0 to M15. So this is the minterm combination. So I am not showing the outputs here, because the output should be 16 in number, there is no space for that. Instead I will draw the circuit directly. So all this says is if 0000 comes on, we want the line D0 to be turned on. If 1111 comes on, we need the line D15 to be turned on, and so on. So one thing you can notice is there are A and B here which are given in green, and there are 4 combinations, this blue, this pinkish one, the orange one, and the yellow one. These are 4 different combinations for different choices of A and B. So in the blue one, A and B is 00, when it's pink, it's A and B are 01, and so on. Let's see how to design some circuit like this. So you know how to design a decoder for this part, right? So if I give you a 2 to 4 decoder, then if it is 0001 1011, if I put a 2 to 4 decoder like this, I will get 4 outputs, right? So I get 4 outputs here, and for each of these I put a 2 to 4 decoder. So you can see that C and D are going as inputs to all 4 of them. So it is a shared input that is going to all 4 2 to 4 decoders. So at this stage what we have is there are decoders. So all these decoders will essentially behave the same now. If you give C and D as input, and if let us say enable was on for each one of those, all of them will, so if M0 turns on, you will see that M4 will also turn on, M8 will turn on, M12 will turn on, and so on. So forget this for a while now. If I had connected, if you look at only this part, they are getting the same inputs, they are all the same circuit. If enable is on, then you will have this issue that based on C and D, there will be 4 lines of the 16 lines we will turn on, right. What we are now going to do is, we are now going to take one step further. So we are going to put another decoder here, it is another simple 2 to 4 decoder, to which we are going to give A and B as input. When we give this, we know exactly one of these lines will turn on. So if A and B are both 00, then line 0 will turn on. If A is 0, B is 1, line 1 will turn on, and so on. So the problem we had was, if it's all C and D connected, and if all of them are turned on, or all of them are enabled at the same time, then you will have 4 of these things turned on, one from here, one from here, one from here, and one from here, for each combination of C and D. Now we are going to control the enable. So when we put this green color decoder here, only one of these 4 outputs is going to turn on, and the output is connected to the enable line. So let us see what happens if the input combination is 00. So I mean 0000. So that's the input to the circuit, 0000. So AB is 0 and CD are 0. So because A and B are both 0, this D0 line of this decoder will be on, which means this blue decoder is enabled. However, these 3 decoders will be, these 3 lines will be off, D1, D2, D3 of this decoder will be off. Since they are going as enable lines for the pink, the orange, and the yellow one, these 3 decoders will be turned off. So A and B being 0 will enable this blue decoder. Now if you put C and D as 0 also, then this is already enabled, C and D are both 0, so M0 will turn on. So now let us go and reason the condition for M10 to be turned on, right. We will go the other way around. If you want M10 to be turned on, first of all this one should be enabled, and the notion of a decoder is, if M10 is on, everything else must be off. So for M10 to be turned on, this must be enabled, all the others must be disabled, which means if you go back here, D2 must be turned on, D0, D1, D3 must be turned off. Now if you go and imagine when D2 will turn on, it will happen for A equal to 1 and B equal to 0. So let us keep this in mind. So for M10 to turn on, then A must be 1 and B must be 0, right. We have that far, right. Then within this decoder, if you want M10 to be turned on, you go and look at the inputs for C and D. What combination must be there for C and D? C must be 1 and D must be 0 for this 1 0 line to turn on. So if C is 1 and D is 0, its D2 will turn on, right. So that is the D2 for this decoder, right. So if you have 1 here and 0 here, this decoder will turn on this line. So we already had A equal to 1 and B equal to 0, and because of the conditions that we want M10 to be turned on, C equal to 1 and D equal to 0, that is the other thing. You go and look at the row 1 0 1 0, then AB is 1 0 and CD is 1 0, go and look at 1 0 1 0, that corresponds to the term M10. So this is just a way to cross check what you have done is correct or not. So this is a simple example of building a complex decoder using a smaller decoder. So you will see that this decoder is very useful later when we talk about what is called memory. So in your computers you have the notion of RAM, right? When we discuss RAM, we will see that this notion of decoders is very handy. We can also use decoders to do a few interesting things. So in this example, let us say we are given two functions f1 and f2, and there are two inputs x and y, and we want to realize this using a decoder. So you have f1 f2 here, and you know that if you want these 4 input combinations, right, you can give it to a decoder, keep it enabled, and exactly one of the 4 lines will turn on, right. So if 0 0 is there, this line will turn on, if 1 0 is there, this line will turn on, and so on. Now what we are going to do is we are going to put 2 OR gates, one for the output f1 and one for the output f2. So what are the conditions under which f1 is turned on? If you notice here, the conditions under which f1 is turned on is if input is 0 1 or if input is 1 0. So that can be captured by checking whether D1 is on or D2 is on. So when will D1 be on? D1 will be on when this is 0 and this is 1, right, and when will D2 be on? When x is 1 and y is 0. So under these two conditions, if you tap those wires and connect to the OR gate, f1 will be on when these two conditions are satisfied. Similarly, if you want to check when f2 will be on, either it should be for minterm 0 or minterm 1 or minterm 2. So we tap those 3 lines, namely D0, D1 and D2, and connect them to a 3 input OR gate. That gives me a function for f2. So in both these things, D3 does not matter. You can notice that D3 is not connected to any of the OR gates, and if you go back to the table, the D3 row is 0. So this row has 0 in both the outputs, so it is not connected. So this is a way in which if you are given a decoder, you can use that to implement other logic circuits also. So you could have done 2 input circuits directly also, but if you are given a decoder and if you are asked to design a circuit with a decoder, the key thing to remember is if you give inputs, the outputs correspond to the minterms, and exactly one of the minterms will turn on corresponding to the inputs. Then you tap all the corresponding minterms, you put them to an OR gate, and you are done. So this essentially captures the AND part of the circuit, and this captures the OR part of the circuit. So you have the AND OR logic, but this AND logic in the decoder can actually produce all the minterms. So this is a very useful circuit. So this is useful in several places. So for example, you might have seen this notion of 7 segment LED displays in your labs, and so for example, if you want, let us say I want to display number 7. If you want number 7, so let us go and look at 0 1 1 1, that is number 7. For number 7 to be turned on, I would like this segment A, the segment B and the segment C to be turned on. If all the other segments are off, that would mean number 7, right. Similarly, if I want number 6 to be displayed, except B, I want everything to be turned on, right. This is the kind of circuit you want. You can go and notice this here. So to capture, if you want to display 6, which is 0 1 1 0, turn on everything except B, right. This is B, turn on everything except B. Similarly, if you want E, right, so if you want, let us say 4, let us say 4, then you want F, G, B and C to be turned on. Let us go and look at 4, B, C, F and G are all turned on, other things are off. So there is a multi-output 4 input circuit. So there are 7 outputs and 4 inputs, and if you want to design circuits for this, then it is much more easier to put a single decoder for all the combinations here. You take all these things and take the combinations here. For each of the output, you put the corresponding circuit. So if minterm 0 or minterm 0 or minterm 2 or 3 or 5 or 6 or 7 or 8 or 9, then turn on A. This segment will turn on only under these conditions. If you want to look at the middle segment G, you can think about it, we will need it for number 2, we will need it for number 3, we will need it for number 4 and 5, we will need it for 6, we will need it for 8. We do not need it for number 0, 1 and 7. So you can see that in the column here, right. So we do not need it for number 0, 1 and 7, or for all the other input bits, input combinations you want them on. So that is what is captured here. So you take the corresponding min terms, put one single OR gate connecting other min terms and you are done. So this is a very nice and simple example for a 7 segment decoder, for a decoder. Then there is this corresponding circuit called the encoders. Encoders are the opposite of decoders. Its output code has fewer bits than the number of input codes. So think about it as generating a code, you have more inputs and you are creating lesser outputs, it is somehow encoding the what input you gave. So a binary encoder is one in which you get 1 out of 2 power n code. So it's, the input will be 1 out of 2 power n values that are possible and the output will be a n bit binary code. So let us see an example here. So this is just like the table that we had earlier except that inputs and outputs are flipped. So D3, D2, D1, D0, there are 4 inputs given to a 4 to 2 decoder and there are 2 outputs. So what we have is, if D3 is turned on, then we will indicate that by turning on both B0 and B1. If D2 is turned on and if the others are off, then we will indicate that by saying B1 is 1 and B0 is 0. Similarly, if just D0 is turned on, we will indicate that by saying B1 is on and B1 is 0 and B0 is 0. So as long as exactly one of the inputs is turned on, the output from the encoder will be one of the 4 combinations, right. So here we have 4 inputs, if exactly one of them is turned on, then one of the 4 2-bit combinations will come here. So encoders typically do not have enable lines and you should ensure that exactly one of them will be turned on. So if you notice, even though there are 4 inputs, we do not have 16 combinations, we have listed only 4 combinations. So at no point in time you can have 0, none of them turned on or more than one of them turned on. Exactly one of these lines should be turned on for this encoder to give a correct output. So this is, in some sense, is the opposite of what we saw in the decoder. So this brings me to the end of this module. So what we saw are 2 really important circuits. Decoders are very useful, we will see them in more detail later, and encoder is just the opposite of the decoder except that encoders do not typically come with enable lines and you have to take care of the condition. If you are going to use an encoder in a circuit, somehow you should take care of the condition that exactly one of the inputs is on, the other inputs are not turned on. You can't have 0 inputs turned on, you can't have more than 1 input turned on also for an encoder. So in the next 2 modules we will see what are called multiplexers. So see you soon.